My name's Max Standen, and I'm here to talk about CybORG, a gym for the development of autonomous cyber agents. The discipline of autonomous cyber operations aims to combine reinforcement learning and cyber defense in order to produce agents capable of defending a computer network from attack. It is challenging to build agents capable of interacting with a computer network due to the large and dynamic state space. For example, we can simulate all the way down to the transistor level. However, this would mean that the state space is unfeasibly large. Even more abstract representations, such as users and files, can still be very large in an enterprise network. It is also very dynamic, as these objects can appear and be added to the network over time. Similarly, the action space in a computer network is very large. As you can imagine, an agent can perform any command or run any program on a computer that a normal human user can. Another challenge that we're particularly interested in this paper is called the reality gap, which is a problem that also affects autonomous robotics. The reality gap is the difference between a simulation that agents learn on and an emulation or a real-world system that the agents actually are tested on. This reality gap manifests itself in that during a simulation, agents can often find shortcuts or particular artifacts within the simulation that they learn to use and interact with. However, those artifacts do not appear in the real world, and so they are unable to be transferred to that new environment. So we've created CybORG, the Cyber Operations Research Gym, to provide a capability for transference between these two environments, as well as to support competitive multi-agent training to facilitate research into autonomous cyber operations. So we contribute this gym, which includes this high-speed simulation, which allows us to use deep reinforcement learning due to its high speed. We also have a realistic emulation environment that utilizes infrastructure as a service to create large real networks capable of running real cyber attacks and defenses to evaluate the performance of the agents. We also can demonstrate the transference between agents trained in the simulation and then can be tested successfully inside the emulation. So of interest to us is the ability to both have a high-speed simulation and a realistic emulation. A lot of previous cyber environments focused on pure emulation to capture the realism of the environment, such as Brawl and Galaxy. However, this prevents us from properly creating reinforcement learning algorithms, especially deep reinforcement learning algorithms. Other approaches use a simulation such as Insight, Candles, and other penetration testing simulations, some of which do support reinforcement learning. However, the lack of emulator prevents us from using these to transfer into real solutions. A modern example is Microsoft's Cyber Battle Sim, which is a simulation that enables node-based lateral movement, similar to CybORG, with a highly flexible state and action space. However, the lack of emulation prevents us from transferring agents that have learnt to interact with this environment into a real scenario. Fileland and some other approaches have used both a simulation and emulation. However, they have been limited in some other ways. For example, Fileland focuses on network level detection and response, while our interest is at both the network level and the host level. CybORG is designed to support a range of deep reinforcement learning algorithms and to test them against a range of scenarios. So we have a scenario file which can be used to specify what hosts exist in the network, as well as their arrangement within the network. Each of these hosts can be defined as an image file, which specifies what users, files, and processes are running. on that host, and they can be arranged into subnets to coordinate how they are able to communicate to each other. The interface with CybORG can be altered to better support a range of different reinforcement learning algorithms. By default, it has a single large results object capable of storing a large variety of data. For example, in this base output, the observation is a large dictionary of dictionaries that contain a lot of key value pairs that contain all of the information that could be observed from the environment. However, to better facilitate deep reinforcement learning, we do convert this into a large vector of floating point numbers through the use of wrappers. In the image below, you can see the OpenAI Gym wrapper, which converts the results object into the observation done, reward, and info tuple that is expected by libraries such as Stable Baselines 3, which we have used to interact with CybORG. The simulator represents the scenario as a finite state machine, and actions are used to transfer between states in this finite state machine. Each action is built from expert knowledge, as well as data collected from real experiments. Here you can see the state of the simulator. You can see that there are 3 top-level objects: the session, the host, and the subnet. Sessions are how agents interact with the environment, and these include things like servers or particular bits of malware that agents use to interact with the environment. There are also subnets, which specify the configuration between the network layout and configuration between hosts. These also can include firewalls to prevent certain traffic between them. And our main object, which is a host, contains a very large amount of parameters, including architecture and operating system, what patches have been installed in the operating system, the files, the users, and the processes that are running, as well as interfaces that link to subnets and events that can be observed by a Blue agent. Our emulation, on the other hand, uses real emulated hardware. We use Amazon Web Service so that we can utilize the infrastructure as a service to scale to large enterprise networks to facilitate a more realistic environment. Agents interact through either Metasploit or Velociraptor. Metasploit is a common red team tool. It has a large amount of exploits and other actions that can be performed quite easily. And Velociraptor is a host monitoring tool that allows the Blue team to observe what's occurring on each host and to interact with each host. Here we have our example scenario. We have 4 hosts, one controlled by the red team or the attacking agent, and one controlled by the blue team or the defending agent. There are 2 contested hosts, a Linux host and a Windows host, in the middle of the environment. In this scenario, the attacking agent has gained access to a network and is now aiming to perform post-exploitation lateral movement to access valuable data on the Windows host. However, there exists some defenses to prevent it from directly accessing this Windows host, so it has to go first through the Linux host. Unfortunately, we were unable to get a successful result from training a blue agent, so we will only focus on the red agent's performance in this paper. So some of the actions that red can perform in order to achieve its goal are lateral movement, which allow it to gain execution control over a different host. It can brute force SSH credentials, or it can exploit services such as the Microsoft's SMB service using the Eternal Blue exploit. It can evade defenses, for example, using autoroute to avoid a firewall. And it needs to perform discovery of new elements of a network, such as port scanning to discover what services are listening, and ping sweeps to discover new hosts in a network. Finally, it can upgrade its execution capabilities by installing new malware, such as Meterpreter. To test the transference between the simulation and the emulation, we've created a deep reinforcement learning agent that learns in the simulator and then acts in the emulator. This deep reinforcement learning is based on DQN, a deep Q network, and it utilizes an LSTM module. This module is important to the learning process because the observations received from the environment are very limited. For example, a port scan might only return a list of open ports and no other information. So memory is very important for learning how to interact with a cyber environment. We also use a branching structure to interact with a parameterized action space. This is due to the very large action space problem and is a way of reducing the complexity of that challenge. We also use a series of masking techniques to avoid the complexity of the large action space. For example, during execution, we use a rules-based mask to prevent the agent from taking invalid actions, such as attacking an IP address it hasn't discovered yet. We also use a masking technique to prevent it from learning on branches of the network that predicted parameters that aren't used. For example, to perform a subnet scan, only a subnet and the subnet action is required, and an IP address doesn't affect the performance of that action, so the IP address prediction is masked out. We were able to successfully train a larger number of agents to actually interact with both the simulation and emulation. So during training on the simulation, all agents successfully learned. We capped the number of iterations at 2,500. However, many completed their training well before this number. And all of them were able to successfully interact with the simulation before we reached this cap. We used a maximum of 20 steps per game, and there was a maximum of 21 independent reinforcement learning agents trained. Each of these agents were then evaluated 10 times against the emulator, and of these 210 evaluations, 139 were successful. As you can see by the left bar, about 4 agents were completely unable to transfer to the emulation. However, a large number, 9, were able to fully transfer their learning across. So this paper introduced CybORG, our cyber operations research gym, to enable the research into autonomous cyber operations. The results we presented validate the effectiveness of transferring agents from a simulation into an emulation. And CybORG assists the research community into starting to address some of these challenges in the autonomous cyber operations domain. Going forward, we would like to improve CybORG by improving the performance and support for Blue agent training to enable more exploration of the competitive multi-agent aspect of cyber operations. And we would like to create larger and more realistic and more diverse scenarios to start to evaluate their performance. If you would like to ask us any more questions, please feel free to contact us, and thank you for listening.